Once we have prepared an asphalt mixture using a trial aggregate blend and then calculated the volumetric properties of the mixture at a corrected asphalt content, we can evaluate whether the aggregate blend is acceptable or will fail to meet SuperPave specifications. We'll go through an example of how to do this using the results of trial aggregate blend 1 that we've been working with in all the previous videos. Recall for trial blend 1, our design traffic level was 10 to 30 million easels. We are using a nominal maximum aggregate size of 9.5 millimeters. And below you'll see the results of our volumetric properties that we estimated at our corrected asphalt content. The requirement for our percent GMM at our end design compaction level is that it equals 96.0%. This corresponds to an air void content of 4%. Our overall target in SuperPave mix design is to achieve 4% air voids at our design compaction level. If our air void content is above 4%, our mixture will be dry and susceptible to cracking. If our air void content is below 4%, the mixture will be too soupy and soft and therefore susceptible to rutting. Therefore, it is critical that we achieve 4% air voids in our asphalt mixture. Our estimated air void content at our corrected binder content was 4% since that was our design objective. Therefore, we meet this requirement of SuperPave. Our next requirement that we need to check is our percent GMM at NMAX compaction level. We see that SuperPave requires that our percent GMM at NMAX be less than or equal to 98.0%. We estimated that our percent GMM at NMAX for our corrected binder content would be 97.46%. Therefore, we meet the SuperPave requirement. The next requirement that we need to check is our voids in mineral aggregate, which we abbreviate VMA. The voids in mineral aggregate represents our effective binder and air void content that fills the space between our aggregate particles. Our requirement for our VMA is a function of our nominal maximum aggregate size. This is because smaller particles have a greater surface area and therefore require more binder than larger particles to coat them. We see that for our nominal maximum aggregate size of 9.5%, we have a minimum VMA requirement of 15.0%. We estimated that our VMA would be 14.54% at our corrected binder content. Therefore, we fail to meet this SuperPave requirement. Next, we can check our voids filled with asphalt, VFA, and see if it meets the target range. The VFA requirement is used to prohibit the use of marginally acceptable VMAs in asphalt mixtures. We see that the requirement for a traffic level of 10 to 38 million easels is the range of 65 to 75%. However, we see that there is a superscript of several footnotes that we also need to check. The only footnote that applies to our mixture is G, which stipulates that for a traffic level greater than 3 million easels and a nominal maximum aggregate size of 9.5 millimeters, the VFA range must fall within 73 to 76%. Therefore, we'll use this range in place of the 65 to 75 included in the table. Our estimated VMA at our corrected binder content was 72.49%. Therefore, we fail to meet this SuperPave requirement as well. The last property that we need to check is our dust to binder ratio, and it must fall within the range of 0.6 to 1.2. We calculated that our dust proportion would be 0.98 at our corrected binder content, and therefore we meet this SuperPave requirement. However, because we failed to meet the VMA and VFA requirements, this aggregate blend is unacceptable.